Meeting is being recorded.
So hello, and so welcome everyone to this week's talk in the virtual geometry seminar on geometry with symmetry. So it's a pleasure to have Tomás Otero Casal from the University of Münster, who will speak on cohomogeneity-one actions on symmetric spaces. So thank you, Tomás, for giving a talk in the seminar.
Yeah, thank you. It's a pleasure to speak in this nice seminar. Today I'm going to speak about some recent developments on the classification of cohomogeneity-one actions on symmetric spaces. So our setting will be the following. We have M Riemannian manifold, which for just the sake of avoiding technicalities, I'm going to assume is connected and complete, and H connected Lie group acting isometrically on the Riemannian manifold. And yeah, also if one wants to avoid technicalities, it's a very harmless assumption to assume that this H is a closed subgroup of the isometry group of M. And well, in this case, the homogeneity of the action of H and M is defined to be the least codimension of H orbits. So for example, here we see the action of a group of screw motions in Euclidean space, the orbits being helices and the z-axis. This is of homogeneity 2, or for instance, the action of the group of rotations SO3 on Euclidean space gives us orbits a fixed point in the origin and spheres around it. So this is an action of homogeneity-one. The orbits of, in particular for homogeneity-one actions, we can think of them as actions precisely which have at least some hypersurfaces as orbits. And the orbits which are hypersurfaces, I will refer to them as regular orbits, and the ones that are not, I will call them, or are called singular orbits. So, I don't know, maybe a couple of reasons to care particularly about the actions of homogeneity-one is that, for example, they are interesting from, they have been used successfully as symmetry ansatz to construct different metrics with special properties, with Einstein, special holonomy, and so on. For example, because you can rescale, take an isometric homogeneity-one action on a given space and rescale the metric along the orbits, or do Chigre deformations and stuff. But another reason, and why I originally came to this topic, is that of submanifold geometry. The orbits of isometric actions have especially nice properties. Some manifolds, for example, the regular orbits of a homogeneity-one action have constant principal curvatures, have constant curvature. They form an isoparametric family of this ambient space M. So maybe it is an interesting problem to fix an ambient space and try to know what are all of the possible actions, homogeneity-one actions on this ambient space. And of course, if one kind of aims to do a classification result, we should clarify what do we mean for two isometric actions to be sort of the same. And in this case, well, there are several notions. For example, you could ask that the corresponding subgroups are conjugate in the full isometry group. In my case, I will fix a notion coming from some manifold geometry. We will say that two homogeneity-one actions are the same or orbit equivalent if the corresponding orbit foliations are congruent. So if they have the same orbits modulo an ambient isometry. And of course, maybe if you want to do this kind of study, you need at least some actions that are with cohomogeneity-one. So this, for example, immediately forces the isometry group of your ambient manifold to be big. And well, since we ultimately want to look at groups, it's always nice to know some information about the isometry group, and therefore symmetric Riemannian symmetric spaces provide an ideal testing ground in which to tackle this kind of problem. So throughout this talk, M will be, unless otherwise stated, a symmetric space G mod K, where G and K are seen to be a symmetric pair. So let me give a brief outline of the different attempts of classifying cohomogeneity-one actions on symmetric spaces. Symmetric spaces can be roughly divided into three categories depending on their curvature. We have the symmetric spaces of compact type, which are compact and with non-negative curvature. Euclidean symmetric spaces, which are flat, and symmetric spaces of non-compact type, which are Hadamard manifolds. The first, maybe arguably, classification of cohomogeneity-one actions on a symmetric space can be attributed to the classical work of Levi-Civita and Segre on isoparametric hypersurfaces of Euclidean spaces. Namely, they were studying isoparametric hypersurfaces, and they showed that an isoparametric hypersurface of Rn is either a hyperplane, a sphere, or a generalized cylinder. And these arise all as orbits of isometric actions. In particular, this provides a classification of cohomogeneity-one actions because orbits always are isoparametric. So that's that. And a very similar result was proven by Cartan soon after for hyperbolic spaces. Also, in real hyperbolic spaces, an isoparametric hypersurface is always an orbit of some ambient group of isometries, and this gives you a classification of the corresponding actions. Nevertheless, this same approach does not work anymore, for example, for sphere. It is well known that there exists isoparametric hypersurfaces in spheres that do not arise as orbits of isometric actions. In fact, Xiang and Lawson and Takagi and Takahashi provided a classification of cohomogeneity-one actions on spheres in the 70s that the classification of isoparametric hypersurfaces was open until relatively recently. Obtaining similar results for symmetric spaces of higher rank proved to be somewhat challenging, but nevertheless, over the last 25 or so years, there has been a series of efforts which now mean that we have a mostly clear picture of how they look. For example, in 2001, Corros gave a complete classification of cohomogeneity-one actions for any irreducible symmetric space of compact type. Also, in the setting of symmetric spaces of compact type, him and Solonenko recently announced some progress on the case of reducible symmetric spaces, but as of now, it's still unpublished. And in the non-compact setting, there's, well, we have both a disadvantage, which is that due to a lack of topological restrictions, symmetric spaces of non-compact type admit a lot of homogeneity-one actions. But as I will explain later, we have an advantage, which is we can work with the theory of the restricted root space decomposition of the isometry algebra, which turns out to be a very useful tool. And this, over a long series of papers by all these people here, which I'm not going to cite individually, allowed us to finally be able to give a complete classification of homogeneity-one actions for any given symmetric space of non-compact type. Here I must remark that this also works for both irreducible and reducible symmetric spaces of compact type. So let me, on the first part of this talk, I'm going to focus on these symmetric spaces of compact type and how do we work with them? Well, so if G mod K is a symmetric space of non-compact type, one can see that the isometry Lie algebra G is a real semi-simple Lie algebra, and one can take G equals K plus P to be by taking the involution at some fixed point, which K is the isotropy of. We can take a Cartan decomposition of the corresponding non-compact real semi-simple Lie algebra such that K is isotropy Lie algebra and P is some complementary vector space that we can identify with the tangent to M at some base point. And then taking a maximal abelian subspace of this subspace P, this gives rise to what's known as the restricted root space decomposition of G, which is a composition of G as a direct sum of subspaces G lambda, where G lambda is the set of vectors in G, such that if we bracket a vector H in A with X, the resulting thing is precisely lambda of H times X, where lambda is some functional defined in this abelian subspace A. And well, this behaves similarly maybe to, let's say, to the root space decomposition of a complex semi-simple algebra, in the sense that we have these bracket relations here. And the difference being that, well, the corresponding, well, I must say, if G lambda is non-empty, or sorry, non-trivial, we say that G lambda is a restricted root space and lambda a restricted root. And the corresponding, like the set of all roots, forms an abstract root system. And the difference with the setting of complex semi-simple algebras is that our root spaces here do not need to be of dimension 1, so they have some multiplicity attached to it, and the root system does not need to be reduced. We could have in principle that lambda is a root and 2 lambda is also a root. But apart from that, the rest of the stuff works kind of similarly. We can define a set of positive roots and a set of simple roots and so on. So the way I like to think about root spaces, maybe I always draw this drawing here with these two pyramids and a line in the middle. The line represents, well, the root space G0, which is the set of vectors that precisely commute with A. The points above the line, by the points above the line, I think about the root spaces G lambda, where lambda is a positive root. The ones below are the root spaces G lambda, where lambda is a negative root. And the points closer to a line above, they are precisely the simple roots. In this way, if we are taking a bracket of some vector in some root space with a positive, with a vector in a positive root space, we are going up the drawing, and if it's negative, we are going down by these properties of the bracket. In particular, if we take n to be the sum of all root spaces corresponding to simple roots, since we can only go up the pyramid, this is a nilpotent subalgebra. And since taking brackets with A preserves root spaces, A plus n is solvable subalgebra of G. And we have the Iwasawa decomposition theorem, which states that G, the Lie algebra, the isometry Lie algebra, splits as a vector space direct sum of the isotropy Lie algebra K plus A plus n. And there's an analog known as the global Iwasawa decomposition at the level of Lie groups, which states that G is diffeomorphic as a manifold to this product K plus A plus n. But K was precisely the isotropy of our symmetric space. So by quotienting by it, we say that M is in fact diffeomorphic to the solvable Lie group AN. And if one takes the pullback of the metric under this diffeomorphism, this gives you a left invariant metric on M. So we can always think of a symmetric space of noncompact type as a solved manifold, a simply connected solvable Lie group with a left invariant metric. And this already gives us the first easy way to construct isometric actions on a symmetric space of noncompact type. Since we have this identification here, we can think about subgroups or subalgebras of this group AN, or the corresponding algebra A plus n, as actions, which precisely because this has no isotropy, gives us actions without singular orbits. In particular, if these subalgebras are codimension-one, the corresponding actions are of homogeneity-one. So is there any nice way, using the properties of root spaces, to construct codimension-one subalgebras of A plus n? The answer is yes. And well, the two easy ones are, well, this identification here induces scalar product on the Lie algebra A plus n, which makes A and n orthogonal. So in particular, if we consider a vector x in A and take the orthogonal complement of this x in A and add the whole n, we get a codimension-one subspace of A, but this has to normalize n. In particular, this thing here is a subalgebra. And the corresponding actions are known as actions or foliations of horospherical type. And as you might guess from the name, this is, for example, how you can construct the foliation of a, say here, picture real hyperbolic tree space by Horus spheres. And the other easy way to construct this is, well, if you suppose that if you take a vector x in a simple root space, since taking brackets with positive root spaces means you can only go up in this pyramid before, and simple root spaces are at the bottom, the corresponding group A plus n minus x, where this stands again for the orthogonal complement, is a subalgebra. And the corresponding actions are known as actions or homogeneous foliations of solvable type. This is, for example, this way you can construct an action on, again, real hyperbolic tree space with a totally geodesic real hyperbolic plane passing through the origin and equidistant hypersurfaces as orbits. And there's this nice theorem originally due to Bernd and Tamaru, and they did it for irreducible spaces and later generalized to also reducible ones, which says that if a cohomogeneity-one action does not have any singular orbits, then it has to have the same orbits as one of these two actions constructed this way. Let me briefly give an outline of how you do this, maybe skipping some details. So since the action does not have singular orbits, it induces a homogeneous foliation on M. And M is Hadamard. And here it seems to be a sort of, I don't know if it's standard, but I've seen this many places, trick. You can sort of use the Cartan fixed point theorem and the structure of your group H to find that there is a subgroup S of, well, here I wrote isometric group, but in fact, if you start with an action of a group H, S can be actually taken to be a subgroup of H, which is very nice. It is a closed subgroup of the isometric group. It is solvable. The action on of S on M is free. And more importantly, S has the same orbits as your original group. So somehow you take a smaller, nicer subgroup, which gives you still the same orbits. And now S being solvable means that its Lie algebra must be contained in a maximal solvable subalgebra of G. And there's maximal solvable subalgebras of real semi-simple Lie algebras can actually be parameterized by subsets of simple roots. And you can give a list of all of the maximal solvable subalgebras of G, but the fact that S acts with cohomogeneity-one implies that this maximal solvable subalgebra cannot be anything. It must be of a very special type, namely it is of the form T plus A plus N, where T is here some abelian subspace of the centralizer of A in the isotropy. And then, also after some work, it is possible to show that you can project this solvable subalgebra S along T. You get, in principle, this should be a subspace of A plus N. But it is possible to prove that this is actually a subalgebra. And in fact, it can be seen that the corresponding subgroup acts with the same orbits as your original action. And after doing some congruence details, you show that X is either in A or in a simple root space. Okay, so far so good, but this procedure of taking subgroups of AN only gives us actions without singular orbits. So how can we construct actions with singular orbits, or how can we study them? And here there's a very nice procedure which was originally introduced by Berendt and Tamaru, which is that you can, under some circumstances, extend actions from lower rank symmetric spaces where it might be easier to construct actions with singular orbits to actions on higher rank ones. So we start with symmetric space. We consider the composition of the isometry, Lie algebra, the root space decomposition, and we take here phi to be a subset of simple roots. And we define now a series of subalgebras which get kind of technical, but don't worry too much about them. We take A phi to be the intersection of all of the kernels of roots in this subset here of simple roots, which roughly you can think of it as being the part of your abelian subspace A, which does not lie under these simple roots. And similarly, M phi you define to be the sum of all positive root spaces corresponding to roots which are not in the span of this subset of simple roots. Here painted in green is the positive root spaces that do not correspond to things in your subset. And then you take G phi to be the subalgebra generated by the root spaces which do lie in your set, in this set of simple roots. And this you can think of as a smaller decomposition, a smaller semi-simple Lie algebra sitting inside your bigger one, generated by this root subsystem here. And well, in fact, if you take the corresponding subgroup of G and you take the orbit through the origin, you see that the orbit of this dark purple thing here is a totally geodesic submanifold of M, which is itself a symmetric space. It has rank the number of roots in this subset, and actually G phi is the isometry Lie algebra of this smaller symmetric space, which is called a boundary component. And there's this theorem called the horospherical decomposition, which states that the ambient manifold M is diffeomorphic as a product of to D phi, this thing called the boundary component, A phi, and M phi. So if you didn't like this, don't worry, just think of B phi as some smaller symmetric space of non-compact type, which is of lower rank, and A phi and M phi, a group which moves sort of this B phi around in a way that you, if you sweep along these A phi and phi orbits, you get the whole M, your original symmetric space. And why do we care about this? Because let's say you have a Cohomogeneity-one action here on your boundary component, we're able to construct this somehow. Well, then without loss of generality, you can assume that it's given by a subgroup of G phi, and you can construct a Savager as follows: H phi capital lambda, which is take your action on the boundary component and add this A phi and N phi. And the corresponding group that you get acts with Cohomogeneity-one on the ambient symmetric space. What are you doing here? So essentially you are taking every orbit here on B phi and moving it along A phi and phi. And so if the original action has a singular orbit, the resulting thing on the ambient space is going to also have a singular orbit. And this group here is what's known as the canonical extension, or this action here, the canonical extension of the action on the smaller copy of your symmetric space. Maybe I'll just state the classification theorem for symmetric spaces, Cohomogeneity-one actions on symmetric spaces of non-compact type, which says that if you have a Cohomogeneity-one action on M, and this Cohomogeneity-one action does have a singular orbit, otherwise it's one of the two from before, your action has to be orbit equivalent to the canonical extension of one of three things. Either you have a boundary component which is irreducible and your action has a totally geodesic singular orbit. And essentially, in this case, you kind of are able to use duality to work with the corresponding actions. And so Bernd and Tamaru gave a complete list for any reducible symmetric space. There's a list of actions that arise this way. These are well known. There's a second thing that can happen. Your boundary component is a product of homothetic hyperbolic spaces, and the group acting is some diagonal thing, which is essentially just the diagonal subgroup. They have, well, since they are homothetic, they have the same symmetry group. And so you take the diagonal, and this acts with Cohomogeneity-one, and also a singular orbit. And then there's a series of exceptions, actions which have a singular orbit, which is not totally geodesic. But these exceptions only happen in either rank 1 spaces, so hyperbolic spaces over some division algebra, or in symmetric spaces of non-compact type and type G2. This is sort of the big theorem that was proved last year by Sanmartín-López and Solonenko, which completed the classification. And maybe I'll skip the proof of this. And so the takeout is, well, for symmetric spaces of compact type, we kind of know the actions. For Euclidean symmetric spaces, we kind of know the actions. And after these recent developments, for symmetric spaces of non-compact type, we know the actions. So a natural question to ask is, I guess, what happens if your symmetric space does not have a type? For example, what happens if you have a product of a sphere and a hyperbolic space. Which kind of things do you recover? And so this is what I will focus now on the second part of the talk, which is what happens on symmetric spaces of, let's say, mixed type. Well, it's standard theory that every single symmetric space, simply connected symmetric space, by taking the ramp decomposition and grouping the factors of the same type, splits uniquely as a Riemannian product of the form M plus, this being a simply connected symmetric space of compact type, a Euclidean space, and M minus being a symmetric space of non-compact type. And so, well, we know the actions here. We know the actions on M plus, on Rn, and minus. So in particular, this allows us to construct easy homogeneity-one actions on the whole M tilde, just by taking a homogeneity-one action in one of the factors and something transitive on the other two. And the question is, are all actions obtained this way? And so do the previous classifications results already cover cover any simply connected symmetric space? And the answer is not, but quite. We found in a recent work with Hiroshi, Tamaru, and Solonenko that there is only one exception of one family of actions which cannot be or is not orbit equivalent to one of these kinds of products. And in fact, the way these diagonal actions are constructed is very similar to how we constructed foliations in symmetric spaces of non-compact type. It's being take M minus a symmetric space of non-compact type and take the solvable model again, and well, you can regard it as a self-manifold, and also Rn acts on itself by translations, so it's also a self-manifold. In particular, if you take a codimension-one subalgebra of Rn plus A plus N, this will give you a homogeneous foliation of the corresponding Rn times N minus. And so the way we construct these diagonal actions is the following. Take a vector E in Rn and consider the orthogonal complement, again, with respect to this induced metric of E in Rn. And take a vector X in A and consider again the orthogonal complement of this vector. And this gives you two codimension-one subspaces of Rn and A, respectively. You sum them together, and then you add the whole of N, and this diagonal thing here, which is just the span of E plus X. And the corresponding action is, well, has no single orbits. All of the orbits are congruent, and in fact is not so difficult to compute, for example, the mean curvature. And here we have the action, projects, as I will explain later, to transitive things on each of the factors. So it does not decompose as a product. Here we see this example. Unfortunately, it's the only thing I can draw in the hyperbolic plane times R. Here, the hyperbolic plane it's represented as a Poincare disk model on the XY plane, and then R is the z-axis, and we see that the orbits of this particular thing, if you look at it at horizontal slices, this looks like a foliation of your symmetric space of non-compact type of this RH2 by horospheres, but these horospheres sort of change radius whenever you move along the Euclidean factor. And so how does one go about proving this sort of stuff? So the setting is the following. We have a decomposition of our Riemannian manifold as a product, and we want to see how the action behaves with respect to this decomposition. So in a slightly more general note, if we have a product of Riemannian manifolds, and we have a subgroup in the product of the isometry groups of the factors, the isometry group of M1 times isometry group of Mn, we can consider this action induces subactions, well, in each of these factors Mi, just by taking the projection onto the corresponding isometry group and making it act on the factor Mi. And here, there's a word of caution. This subgroup here, isometry group of a Riemannian product, is generally larger than the product of the isometry group of the individual component. So if you do this for general manifolds, maybe you should be slightly careful about this. Nevertheless, if we have this inclusion here, the orbit of H through a point P1, Pn, it's always contained in the orbit of the projection in P1 times the projection action of the orbit of H through Pn, etc. And in particular, this means that you have here an inequality of dimensions. The homogeneity of the action on the whole ambient space is always greater than or equal than the sum of the homogeneities of each individual projection action. And, well, maybe here there's a lemma which I told at the beginning, kind of white lie, said that this should be obvious. Maybe if H acts with homogeneity-one and M1 times Mn is simply connected, equality in 2 implies equality in 1. And here the trick is, at the beginning, I said that, I was going to take closed subgroups, so orbits are embedded as manifolds, but when you are taking the projection, if you allow to have non-compact factors here, the corresponding groups may fail to be closed, and so the orbits of the projection actions, in principle, could be only injectively immersed. You don't have that they are embedded. So maybe here you could have this inclusion, but not that this is not a continuous map or a smooth map. But anyway, for homogeneity-one actions on simply connected spaces, this works perfectly, and so we have 2 options. This is the homogeneity is one here. Either we have that one of the projection actions is of homogeneity-one and the rest are transitive, which means that, well, then H has the same orbits as some product, the product being precisely the projection, the product of the projection actions, or all of the projection actions are transitive. in which case you say that this action is diagonal. And so let's go back to our setting of simply connected symmetric spaces. Take fix the decomposition of m tilde as m plus times Rn times m minus, the compact Euclidean and non-compact factor. And in this case, we have that the connected components of the whole space m tilde splits as the product. So in particular, every connected subgroup of isometries induces actions on the individual factors. So either these actions are all or some transitive and the action is diagonal, or some projection action is of Cohomogeneity-one. Then maybe I'll do here quick thing, which is, well, this is not that easy to have that all of the projection actions are transitive, because, for example, say that you have a compact factor and you have a group whose projection action is transitive on m plus. Then there's this result of Montgomery, which assures you that, well, since m plus is simply connected and compact, there has to be, in fact, a compact subgroup of H, which is still transitive. Here, K. But now, by the Cartan fixed point theorem, this K has to fix a point on this Rn times m minus, because this is a Hadamard manifold. In particular, if you have that an action is transitive on this Rn times m minus, it will be transitive on the whole ambient space, because you can sort of move a point to PQ to some PQ, with this being the fixed point of the action of the compact group. Is you can move any point to this. You can choose what point you move to in the non-compact factor, this Rn times m minus, and then you can move around using the compact subgroup, which leaves the Rn times m minus alone, and so the action has to be transitive. This is diagonal actions can only happen in Rn times m minus. And this is some great news. And why is it? Because then, well, as I kind of hinted before, this is a Hadamard manifold. This is there's a model of it as a solved manifold. So one kind of can play the same tricks or the same game as we did with symmetric spaces of non-compact type, but this time for actions on Rn times m minus. So for example, if we have an action with no singular orbits, we do the same argument as before. H can be taken to be solvable and act freely. Since it's solvable, it's contained in a maximal solvable subalgebra. Again, these are not difficult to find out how they look like. And they are of the form T plus Rn plus A plus N, where T this time is a abelian subspace on SON plus the centralizer of A in K. But yeah, exactly sort of the same thing as before. You project onto this solvable model the algebra, which in principle should only be, you take the projection of H, in principle this should only be a subspace, but you can actually prove that it is a subalgebra And the action, like this subalgebra, has to be of this form HEX that I wrote before, and the action of the corresponding subgroup has to have the same orbits as H, assuming the action does not decompose. Otherwise, you will get a product. And for actions with singular orbits, you can again make use of this extension from lower rank, that with a slightly different flavor. The same way you extend actions from a boundary component to the whole, to a symmetric space of non-compact type M minus, you can easily do from Rn times B phi to Rn times M minus. This just add the same subalgebras as before, and you extend the action the same way as before. And in particular, we are able to prove the following lemma. If H is a subgroup of isometries here, which acts with a singular orbit, and the projection, well, here I write the isometry group of Rn as SON times Rn, here the just rotations times translations, and G minus isometry group of the symmetric space of non-compact type. And if this action has a singular orbit and the projection onto the isometry group of the non-compact factor is not the whole thing, then you can see that this action can actually be obtained by extension from lower rank. And moreover, the action is going to be diagonal if and only if this smaller action is. So we are able to apply this process recursively to get a very useful assumption, which is that the projection of our group to the isometry group of the non-compact factor is indeed the whole thing. And how do we exploit this? So since our group is not the whole thing, because it acts with cohomogeneity-one, it must be contained in a maximal proper subalgebra of the whole isometry Lie algebra. But the whole isometry Lie algebra has here on the first summon an abelian ideal, which really doesn't like the fact that G minus is semi-simple. So a maximal proper subalgebra inside this thing always is of this form, E1 plus G minus, where E1 is a maximal proper subalgebra inside SON plus Rn. But now, if we assume that our action does not decompose, the corresponding subgroup of isometries of Rn has to act transitively, because the projection action is transitive. And using some classical results, particular, I guess, of Alexeyevsky, it is possible to explicitly describe how this subalgebra E1 looks like. And so the thing is, H this time must be contained, because this, well, E1 plus G minus still acts transitively. It has to be contained in some maximal proper subalgebra here. But again, from this result of Alexeyevsky, we see that E1 has an abelian ideal, which really doesn't like to be together with a non-compact semi-simple Lie algebra. And so any maximal subalgebra inside here, it is of the form E2 plus G minus, where again since our action is transitive on the Euclidean factor, the corresponding subgroup has to be transitive on Rn, and so you can do this over and over and over. It so far has been the trick that I've used today to construct an infinite chain of maximal proper subgroups, EI times G minus sorry, here there's a mistake, which should be H is contained inside of them. But here, well, we clearly have a problem because this chain of maximal subgroups, you should be able to construct it forever, but well, the symmetry group of Riemannian manifold has finite dimension, and so this is a contradiction, right? An action which does not decompose by this argument cannot have a singular orbit, and this is how we prove this sort of decomposition theorem. And yeah, I think I've run out of time, so thank you.
Thank you very much, Tomás, for this very nice talk. And so, well, we're open for questions. So are there any questions? Here's open the chat. So I have just a few questions. So I mean, this existence of the, like, if all are diagonal, then you get this Rn cross M minus, right?
Yeah.
So I mean, this seems very rigid, right? Is that this existence of the all diagonal actions? Is that, and then this M minus, you said it has to be an Adamard manifold, right? That's,
yeah. This is in general, I guess. For example, if you have, again, I'm always going to assume simply connected, just because by the random decomposition you can assure that things induce actions on the factors. If you have a compact simply connected Riemannian manifold and a Hadamard manifold, you cannot have by the same argument as before, you cannot have a group which induces transitive actions on both things unless the whole group is the action is transitive on the product, right? So you cannot get diagonal things. This seems to be like purely topological, or I guess not purely topological, because you need Kerdan's fixed point theorem, but somehow a fight between the topology of the compact factor and the non-positive curvature.
Okay. Thank you. And so I'm not sure if there are other questions. So I think we're about to finish the hour. So I'm going to just close the talk, but we can stay longer for further discussions. And well, so I want to thank you again, Tomás, for the talk, and thank you everyone for joining. And I hope to see you in sort of the upcoming talks. So thank you.
Thank you.